Welcome back to The Explainer. We usually think about oil production as this big mechanical process, actively pumping crude out of the ground. But what if I told you that deep beneath our feet, there are these powerful natural engines already doing the heavy lifting, pushing that oil right towards us? Today, we are diving deep into the hidden forces that make it all happen.
It's a really good question, isn't it? I mean, oil isn't just sitting in some open pool waiting for us to stick a straw in it. Nope, it's trapped inside porous rock under just immense pressure, sometimes miles deep. So, what on earth provides that initial powerful shove to get it moving out of that rock and up a well? Well, the answer lies in what engineers call a reservoir drive mechanism. Yeah, it's a technical term, I know, but the idea behind it is actually pretty simple. These are the natural engines, powered by physics, that literally drive the oil out of its home. There are three main types, and trust me, each one works in a fascinatingly different way. Okay, so first step is the most common engine of them all, the solution gas drive. And to get your head around this one, all you need to do is think about something you've probably held 1,000 times.
Exactly. A shaken soda can. Inside that sealed can, the carbon dioxide is dissolved into the liquid, right? That's because of the high pressure. Well, an oil reservoir is just like that can, but on a massive scale. Deep underground, that immense pressure forces natural gas to dissolve directly into the crude oil, just like the fizz in your soda. So, what happens when we drill a well? We've basically just popped the tab on that giant underground soda can. As oil starts to flow out, the pressure in the reservoir drops. And that pressure drop lets that dissolved gas come rushing out of the oil, forming millions and millions of tiny bubbles. And as all these bubbles form and expand, they create this powerful fizzy force that pushes the oil around them toward the well. It's literally the reservoir's own carbonation doing all the work. All right, now for our second engine. This one uses that exact same gas energy, but in a much more organized way. This is the gas cap drive, or as I like to call it, the piston. So instead of the gas being dissolved inside the oil, in this scenario, there's a huge cap of free natural gas already sitting right on top of the oil layer. It's been trapped there by the rock for millions of years, creating this massive high-pressure bubble just waiting to expand. So how does this piston actually work? Well, as we start producing oil from below, we create empty space. And that high-pressure gas cap immediately expands downward to fill that void, pushing the entire column of oil ahead of it. This is a huge advantage because it helps maintain the pressure in the reservoir, which keeps the oil flowing way more easily. So let's make this super clear. The crucial difference is just the location of the gas. With the solution gas drive, the energy comes from bubbles forming within the oil. It's chaotic, it's fizzy. But with the gas cap drive, the energy comes from a big, unified cap of gas pushing from above. It's a much more orderly and efficient push. But there's a natural engine that can be even more powerful than gas. Let's get into our final mechanism, the water drive. You could also call this one the flood. This happens when an oil reservoir is connected to a huge, water-filled rock formation called an aquifer. And you can pretty much think of it as the oil field sitting on top of a vast underground ocean. And you guessed it, this massive body of water is also under a whole lot of pressure. This one is all about displacement. As we produce oil, the pressure in the reservoir drops. In response, the compressed water in that aquifer expands to fill that low-pressure void. This creates an encroaching wall of water that acts like a slow, steady, and incredibly powerful flood, physically sweeping the oil out of the rock and pushing it toward our wells. Now, the water drive is typically the most efficient natural engine out there. But there are a couple of catches. It needs a huge connected aquifer to supply all that power. And it's what we call rate sensitive. If you produce the oil too fast, the water can't keep up. The pressure drops, and you lose the whole effect. It's a real balancing act. So we have the fizz, the piston, and the flood. But how do they actually stack up against each other? I mean, how much of the oil that's in the ground can they really push out? Let's take a look at the efficiency scorecard. First step, our standard solution gas drive. On its own, its recovery is, well, it's surprisingly low. We're talking just 2 to 15% of the oil. That fizzy, chaotic energy just burns out really fast, and it leaves a ton of oil behind. But here's where things get really interesting. In some reservoirs, gravity can actually step in to help. See, as those gas bubbles form, they naturally want to rise, and if the rock lets them, they can migrate upward and collect at the top, forming what's called a secondary gas cap. And just by doing that, they transform a chaotic fizz drive into a much more efficient piston drive. This effect, it's called gravity segregation, can dramatically boost recovery, pushing it all the way up to 20, maybe even 40%. What a huge improvement, and it's all thanks to good old gravity. But the undisputed champion, the king of natural recovery, is the water drive. Under the right conditions, this steady, powerful flood can recover up to 50% of all the oil in a reservoir. Half of it. So when you put it all together on a chart like this, the difference is just massive. You can see the basic fizz of a solution gas drive at the bottom, the huge improvement you get when gravity helps out, and then way up at the top, the incredible performance of a strong water drive. Of course, nature is rarely so neat and tidy, right? The reality is that most reservoirs aren't just one type. They're what we call a combination drive. So you might have a gas cap pushing from above and a weak water drive pushing from below, all while solution gas is fizzing out of the oil at the same time. It's this complex dance of all these forces at once. So as you can see, these natural engines are incredibly powerful. They do all the initial hard work for us, totally for free. But even the best one, the water drive, leaves about half the oil behind. So that brings us to the crucial question. Once these natural forces have given it all they've got, when the pressure finally runs out, what do we do to get the rest? Well, that's a story for another time. Thanks for joining me.